Hello. A few things before I begin the lecture. Change the camera. I did so midterm 3 and all the grades are posted, right? And homework 9A is due on Tuesday. There's a correction in here. So this is a correction. In figure 1, swap capital mass M with small m in figure 1. So the capital mass and small m is swapped very much in the figure. So make sure you take care of that correction. And we will have a homework 9B. It's still visible? Yes. November 17th, which is a Tuesday. That's 1 week from there. And we have the midterm exam right afterwards. It's November 19th. And just to complete the list, final exam, relatively far, on December 10, Thursday at 12:30. I have dropped some extra credit problems, and I'm not sure if I've dropped homeworks also or not, but make sure you realize that from this point on, the grades that will change will be relatively less. There's a lot of grades that has been collected already. So be aware of that and be judicial when you're trying to work hard to change your grades. If you have to discuss about your grades, feel free to contact me. This is the right time to talk about it best now that we have just uploaded the grades. Any questions as such? Anything specific to the course or anything in general?
Shajesh, I noticed on homework 9A, there's, let me see, on problem 4, M3 is listed twice rather than having like M1, M2, and M3. So I don't know.
Tell that again. Is there another typo? Okay.
Yeah. On question number 4, homework 9A on the diagram.
Okay, give me a second. Let me try to reach there. Yeah, go ahead. Homework 9A. On problem 4, you said?
Yes.
And what is oh, you're saying M1, M2, M3. Oh, yes. Go clockwise. Yeah, let me draw that diagram. Yeah, that's again a typo.
Yeah, and I assumed it was just clockwise, but I just thought I'd let you know.
Yeah, it's a good point. Like it can be confusing. Thank you. So let me just move this and so that I can see my, okay. So this is the diagram. So again, there is, so this is another correction. So that's M1, M2. So that's the correction. M3 and M4. Is that clear? Thank you very much for pointing that out. Yeah, that helps. Let me close this. Any other questions you can think of? Okay. We were doing rotational dynamics. Basically rotational motion of rigid body. So let's call this rotational dynamics for rigid bodies. Of course, even if you have one single point object, that also qualifies as a rigid body because then it says only one object in there. Is that readable? Last time there was like readability was an issue. This time I did zoom in as much as I can. So hopefully it is okay. Let me know if I have to do something else. Okay, we are talking about rigid bodies. So what are rigid bodies? Right. Points inside the body do not move with respect to each other. Points inside do not move, right? Do not move relative to each other. Just say relatively. So that's a rigid body. Any solid object typically belongs to a rigid body that doesn't deform as it moves. We did rotational kinematics. We said that is delta t. Then we said angular displacement, delta theta. It's supposed to be a vector, but it's always that we are going to be having a fixed axis around which it will be moving. So there is only one quantity there. So it's like motion in a one dimension, linear motion in one dimension. So we are going to be talking about rotational motion about an axis which remains fixed, which is not necessarily true in general motion. Right? So that's angular displacement. Then we had angular velocity, which was omega, and so that's equal to delta theta over delta t. And we had angular acceleration, omega over delta t. So that's the four quantities we introduced. It should be compared with, it's a good analogy to have that in linear motion, this is delta x. If it is just in one dimension, we don't have a vector there. And we have velocity. This is just linear displacement or translational displacement, translational velocity or linear velocity, which is delta x over delta t. And acceleration is change in velocity over change in time. So this is called linear kinematic motion, the rotational kinematics. And from that point on in linear motion, what we did was we wanted to ask what causes the acceleration. That was the primary goal we had. And it was Newton who pointed out first time that acceleration is proportional to the force and inversely proportional to the mass. So Newton's law can be written in this form. Acceleration is equal to sum of all the forces. So you add up all the force. So let's say there's F1 plus F2 plus 1. This should be vectors. These are supposedly vectors, but if everything is moving in a straight line, then I don't have to worry about the vectors. And divided by the mass. So if we specifically ask if we interpret acceleration as a non-trivial motion, then force helps the motion, and the mass does not help the motion. It's inversely proportional to that, so it resists motion in that sense. And we would like to ask the same question with rotational motion. So that is alpha, angular acceleration. So if something is moving in a circle, how quickly it is picking up the angular speed is decided by angular acceleration, and we would like to ask what helps it. And in the last class, we pointed out that torque is something that helps angular motion. So instead of the force, we had the rotational analog of force, and that was torque. So there are many torques possible. So for example, if you have a door and there is an axis coming out of the board, so this represents a door, and you could be exerting a force on it. So this force does not completely contribute to the torque in the sense that there is a component along the door, and there is another component which is perpendicular to the door, and it is only the perpendicular component of the force that helps rotational motion. So often it is called the moment of the force. It is given by r sine theta, and we did examples on that. So that's torque, and there could be many forces acting on this, right? So there could be F1, there could be F2, and so on, and that's your axis. So that's your axis. We would like to know what determines the motion. It's surely the torque due to force 1 plus the torque due to force 2, and so on. Right? Very similar to the forces adding up. And now we would like to ask what resists the angular motion of the door about its axis. Surely there is going to be mass. We can expect that if the mass of the door was very heavy, then rotational motion will be more difficult to achieve. So surely there is a mass in there, but we also intuitively we can see that if this door, more mass was actually concentrated on the outer side of the axis. That means if this was much heavier, like imagine a door which is extremely heavy on this and very light on that end, and another door, a similar door, which is extremely heavy on the axis end and very light on the other end. And we could ask which one is more easy to rotate around, and it will turn out that it is actually this one is easier over that. So it actually depends on radius also. So we would like to investigate that. So for now, let's just call this I. We're not specifying what exactly I is. So this is the inertia that is associated with rotational motion, exactly like mass is the inertia or what resists motion associated with linear motion. This will be the inertia associated with rotational motion. So let's name this. So let me change this. So we want to define I as moment of inertia. And we will sometimes also call it rotational inertia. Rotational. Is what resists rotational motion. What's the definition for this? I already kind of gave you a hint that it depends on the radius, but what for a rigid body, what is the radius? So let's give a definition for I, moment of inertia. This is going to be, remember your definition for center of mass, just to remind you. So this was center of mass. That was sum over I times all the masses, individual masses, and then you multiplied x with it, the position of each mass, and then you divided it out by all the masses, sum of the masses. This is a relatively similar concept, except that instead of x, you want to multiply it by x squared. So we're going to define our moment of inertia, and there won't be any denominator. Just that was to set the dimensions correct. So here we are going to define moment of inertia as, we'll do examples to clarify this. Individual masses, if there are many masses, and position of each of the mass with respect to the axis. So this time we will call it Ri, and this will be Ri squared. So what is Ri in here? So mass is clear what it is. Ri is distance of mass Mi with respect to from the axis. From the axis. There is an axis. If we are talking about rotation, there has to be an axis, and each mass has a distance. How far is it from the axis decides what's your Ri, and it is a perpendicular distance from the axis. So let's see how actually these distances or how the distance from the axis actually resists motion. So let's do an example for that. Okay, so let's consider an example where we have a very light rod. So this is a very light rod. That means it's a massless rod. And let's have two masses attached to them. So this is M2 and that's M1. Let us say M1 is equal to 10 kg and M2 is equal to 100 kgs. I put two significant digits in M1 with the dot in. And now let's try to rotate this. So if we have a, let's say this is a rigid rod, even though it is massless, it is having sufficient strength that you can actually, if I lift this, that also gets lifted. So it doesn't bend or deform, or one doesn't, when you're lifting M1, M2 also lifts with it as much as it can. And now we want to rotate this about an axis. So I haven't specified the axis. So let's say the axis is going through this point, or going through one. So let's say example, so case one, case one is axis passing through M1 and coming out of the board and out of board. And let us say, given that I provide a torque to this particular system. So we have an axis here. So there is an axis right on top of M1. And I try to rotate this, and I don't specify where I'm exerting the force. If I have to rotate this, I have to actually exert a force somewhere. But I do not specify that, primarily because I want to keep my torque fixed. So let's say torque is fixed. So torque is fixed. Then we have the Newton's law in the analogy of that in rotational motion suggests that angular acceleration will be equal to the torque, which is kept fixed, divided by the moment of inertia associated with it. So that's I. And let's calculate this angular acceleration. I need to give you some distances. So let's say this is 100 centimeters. Let's say this is 0 centimeter. That's somewhere here is 50 centimeters, and that's 100 centimeters. And somewhere here will be 20. That's 20 meters. So the moment of inertia associated with about 0.0 would be, so I would be equal to, before I can calculate this, I need to calculate I. So that's sum over mi times ri squared. So there are only two masses. So I have to ask how far are each of the masses from the axis. So that's m1 r1 square plus m2 r2 square. Right? There's only two distances involved. M1 is 10 kg, but what's the distance? R1 is the distance from the axis. The axis is at the position of M1 itself. The distance between M1 and the axis will be 0. So that's 0 square. Plus M2, which is 100 kg, times R2. How far is it? It's 100 centimeters. Let's convert that to meters. So that's 1 meter square. So 1 meter square. So I converted into meters. That's 0. That's 100 times 1. So that's 100 to 2 significant digits. So that's so that will be 1.0 into 10 raised to 2. And what's the units of moment of inertia? Kg meter square. So that's kg meter square. And what's the interpretation? That's the amount of resistance the system will provide to any motion that is going to be caused by a torque. But that doesn't help much because this is a number randomly we gave a number. So we need to have a relative moment of inertia. So let's do this about the other axis, right? Let's keep the axis on the other extreme end and see what's actually the moment of inertia. So that was case 1, and I should also calculate alpha, right? So before I proceed, so let me calculate the angular acceleration. Let's say torque is fixed. So let's say torque is equal to 1. I just keep it 1 Newton a meter. Torque is force times distance, and there's a sign of angle between the distance from the axis and the force itself. But I'm saying that everything is set 1, and I have not specified precisely how you achieve that. So that's 1 divided by 100. Right? So that's 0.01. And since there are 2 significant digits, I should add a 0 there, right? Trailing zeros are significant whenever we write it as a decimal. And that's radians per second square. So the idea is if there was so much of moment of inertia, there is so much of radians angular acceleration. But what if I increase this or decrease this? What happens to the angular acceleration? So let's do case 2 just to have a feel for what this means. Case 2, and I should move the code. We do this again, and this time I again draw this. So this is your M2, that's your M1, and this time the axis is down there. that's your axis. That's your axis. And you want to rotate it about that axis. Again, you calculate I. That's m1 r1 squared plus m2 r2 squared. m1 is 10 kgs times r1 now is 1 meter. So that's 1 meter squared. And m2 is 100 kgs. And clearly, the distance is 0. That's 0 squared. And that's 10. So it is 1.0 into 10 raised to 1 kg meter squared. Clearly, the moment of inertia is less in this case. That's because more mass, the massive object is right on the axis. So you're not really moving it around significantly because it is very close to the axis. So you can also imagine if you're farther from the axis, you're actually moving a farther distance in the same amount of time, right? Because the circumference, the angular displacement is the same. So the arc length will be larger. So that's another way of interpreting the same idea. What about the angular acceleration now? This is torque over moment of inertia. Torque, we keep it the same. So that's 1. Because we want to keep torque the same and then ask what is that angular acceleration. And this time, this is 1.0. So that's 10. So instead of 100, this is 10, and that's 0.10 radians per second squared. Earlier it was 0.01, so this was 0.01. This time it is going to pick up a faster angular acceleration, so it is going to accelerate in a faster manner. So it will start rotating with a larger speed very quickly. So that's the idea I wanted to convey. That now there are two concepts, torque and moment of inertia, and there is an angular acceleration. So these are the three concepts. Force, this is the rotational concept of force, this is the rotational concept of mass, and this is the rotational concept of acceleration. And from that point on, you can do most of what you try to do in the context of Newton's law. Except we should do one more point. All the moment of inertia I talked about here is for discrete objects, right? That is m1 here, these are point objects, m1 here, m2 here. But typically, when you're talking about rotations, we can talk about a disk, right? If a tire is rotating in the car or in a mechanical machine, then that's usually a metallic disk, and that's a rigid body. So we want to talk about the moment of inertia of some rigid bodies, and we won't be able to derive that here. We will have to accept them as they are. So these are some of the this is moment of inertia of rigid bodies. Rigid bodies. Some of the rigid bodies. It depends on the axis also. This is so first let me say the object. So I'm going to list a few objects. So this is object. And it is necessary that you specify the axis. As we saw it in the very simple example we considered, where is the axis determines how much is the moment of inertia. And here I will list the moment of inertia itself. So let me, and some comment also, right, what this is. So comment maybe. So let me draw a diagram here. So this is a cylinder. So this is a cylinder as seen from the top of the board, but this is a cylindrical shell. This is a cylindrical shell. That means to say that all the mass is concentrated on the extreme part of the radius. It's not a solid cylinder. Solid cylinder will be when the mass is completely occupied within or from the center to the radius, it is completely filled. But here it is a shell, so it is only in the outer part of the or we can say think of it as a rim, right, or a bicycle wheel, right? Most of the mass is at the outer end. So example is bicycle wheel, right? Bicycle. What's the spelling of bicycle? Bicycle. Is that correct? Bicycle wheel. Where most of the mass is at the outer end. The axis of this object is as represented here. So that's your axis. So axis is the, so where is the axis? This is the symmetry axis of the cylinder. Like if you think of this as a cylinder, there is an axis associated with that cylinder, and we are keeping that as the axis. In that case, the moment of inertia is equal to exactly the mass of the m is the mass of the cylinder times the radius of the cylindrical shell. That's mr squared, and that's all there is to it. So I should actually specify the radius r. That's your r. Better diagram actually. Change this. Make it bigger. So that's your radius r, and that's your shell. And the axis is coming out of. So that's your m is the mass. Everywhere here, m is mass. Total mass. That seems to be very similar to the definition we had earlier, except that there is no summation here, right? There is only one cylinder, and that is just mass times r squared. The second example we will have is a spherical shell. It looks very similar because how do you differentiate between a sphere and a sphere and a cylinder on a two-dimensional plane? So let's say this is, so that's your sphere, and this is an axis that's it. Sphere and axis is a diameter, right? So axis is diameter. So axis is something passing through the center of the sphere. Again, let's keep radius r to be the same, and this is spherical shell. So axis and the object both matter. And I comes out to be equal to, in this case, 2 by 3. There's a factor of 2 and a 3 times mr squared. Notice that 2 by 3, it is good to notice that there is a 1 there. 2 by 3 is nothing but 0.7. 20 divided by 3 is 0.666, and it keeps repeating, so it's approximately 0.7. Where do you get this factor of 2 by 3? It is very similar to how you get the factor of 4 pi by 3 for the volume of a sphere. If you have ever wondered where that comes from, usually it takes a good amount of work to actually prove that it is 4 pi by 3. And at this stage, since we don't have any abilities with calculus, we will leave it alone. And at this point, we will just accept that the moment of inertia, this is a geometry, this is decided by the geometry of the object, and it is a geometrical concept, moment of inertia. It's 2 by 3 times mr squared, pretty much like the volume of a sphere is 4 pi by 3. Similarly, we will have to remember this. This information is also there in your textbook for important geometries, but most of the time we are having open resource, open book exams here, so you won't need this in your test or anything. But you should be comfortable enough or fluent enough to be able to search in the right place so that you get this information at the earliest whenever you need it. That's two of the geometries we will talk about. We will do two more examples here. The third one is again a cylinder, but this time a solid cylinder. Let me specify this as a solid cylinder. So that's a solid cylinder. So this is an axis is again about symmetry axis. So this is a solid cylinder. Am I still within the? Yes, one more I can go. So solid cylinder. And the moment of inertia for a solid cylinder is 1/2 mr squared. One more example. And next one is a solid sphere. So this is a solid sphere, and the axis going through the diameter again. So diameter, so that's like Earth, right? Earth is an example of a solid sphere, goes through diameter. Now that's solid sphere. And again, it helps to notice that 1/2 is 0.5. As I'm going down in these examples that I'm listing, I'm specifically writing that in a particular order. This has the highest moment of inertia, cylindrical shell. Then comes spherical shell. Then there is solid cylinder. And the solid sphere has the least amount, and that's equal to 2/5 mr squared. And 2/5, remember, if you were to calculate, put that in decimal, that's 0.4. So 1, 0.7, 0.5, and 0.4. These are the four examples we will typically work with in this course, but it is also useful. Just two more or one more example. Let's say if I have a rod, right? If I just simply have a rod, that's also a good example to keep in mind because often it comes about in daily life. And then I have to specify what is the axis, correct? So that's your rod, right? That's your rod. And let us say the axis is exactly perpendicular, passing through the rod and perpendicular to the rod. So this is perpendicular. Rod. There's a length I need for this. So this is the length L of the rod. And so this is a rod, let's say. And the moment of inertia is 1/12 ml squared. This time it's not the radius, it is the length of the rod that comes in. So it is 1/12 ml squared. Again, where do all these numbers come from? It comes from calculus. We don't, it's exactly like a sphere. What is the volume of a sphere, or what is the area of a disk? All those quantities has to be, you add up all these tiny, small areas associated with a volume or an area and add them all together, which involves what is called integration. But we don't want to use spend time on deriving those things. We will just use these factors. More than that, more than the specific numbers, what we are interested in to notice is that certain geometries have larger moment of inertia compared to other geometries. So if we are trying to rotate something and you want larger angular acceleration, we just now saw that moment of inertia tries to resist rotational motion. So you don't want to use large moment of inertia, you will use small moment of inertia. Sometimes masses are good, so you want to keep more mass. Sometimes it gives stability. In that case, you will go to the other and get the higher moment of inertia. So you want to bargain between, or first you want to decide, are we interested in more moment of inertia or less moment of inertia? And this gives you an idea of which geometries have larger moment of inertia and which ones have smaller. the main idea is that how much mass is closer to the axis or away from the axis. Like if you have a shell, most of the mass is spread out away from the axis, so you get more moment of inertia. If the same mass is distributed on a solid sphere, there is a lot of mass closer to it also. In that sense, you've lost some of the moment of inertia. So that's the basic idea in here. And based on these concepts, now let's do some examples that really involve torque and angular acceleration. Erasable. The first example we will do is that of an Atwood's machine, which was this was an example we worked on some time ago while we were doing linear motion. So we had an axis, and at that time we actually ignored this motion of this pulley, if you want. So we had a pulley, and there was a mass m that was hanging onto that, and there was another mass m2 hanging onto that. So let's say this is m1 and that's m2. And now we say there is a pulley that can actually rotate. At that time, while we were doing linear motion, we did not want to complicate our understanding with this rotational motion. So we said the mass of this pulley was 0. That means to say that even if it was 0, that was not really significant as far as the analysis went. But now we say there is a mass of the pulley, m3 is the pulley. So it's a mass of the pulley, and there is a radius r also associated with it. So let's say that's radius r. First, let's go ahead with masses m1 and m2. We know this very well. And by the way, we still keep the tension in the string to be the same everywhere. That means to say we keep massless rope. So rope is, or string is massless. And we will not be able to take off that restriction in this course, but it can be done with a little effort in an advanced analysis of this problem. So we still have massless ropes, but we do have the pulley to have mass, and there is friction now on this pulley itself, because that is necessary. Because if I'm pulling on the rope, and if it was frictionless pulley, then it will just slip off, right? If I want to actually make the pulley move with the rope, I need friction that will do the job. So we will assume that pulley is perfectly rolling. So pulley is perfectly rolling. What does that mean? It means that how much ever the string moves, the pulley also moves. There is a chance that this can slip. The pulley can slip between, the rope can slip on the pulley. That's not happening. That's what it means. And I also have to assume that on the axis, right, on the axis, there could be friction there. So the axis is frictionless. Axis is frictionless. All these constraints can be removed, but we are simplifying the analysis so that all this doesn't come into picture. The axis is frictionless. So these are some of the ideal scenarios. So whenever you see these problems in this course, we have assumed these scenarios. Okay, so having said all that, now we can do the analysis of the forces before we do the torque. So this is m1g, and that is a force of tension. We've done this before. That's your force of tension. And let's say this was tension T1. And this is m2g. and this was force of tension T2. Earlier, 3 weeks back, when we were not dealing with the rotational motion, we argued that the force of tension T1 here has to be exactly the same as the force of tension T2 on the other side. But that's not the case anymore when there is a pulley which has a mass associated with that, because this only connects with the pulley. Right? Now there is an intermediate mass in there, so it has to talk through the pulley to the mass M2. So the only thing we can say is that the tension on the rope at this point will be T1. But we cannot say the same thing out here. And there will be a similar tension here, T2. So notice what is happening. This piece of the rope, one pulls the mass M1 up, and the other side pulls the pulley down. And the same thing on the other side, this part of the rope pulls M2 as far. When it comes to M2, it is pulling it upward. When it comes to pulley, it is pulling it downward. Right? That's the job of the rope. If the rope had mass of its own, then this becomes an intermediate object, and we have to analyze that also, but we are simplifying that whole analysis in here. Okay, with that information, so let's begin by analyzing what is or let's finish off with the linear motion first of all. So this is going to be accelerating down. So that's A. And it's going to be the same acceleration that's going to be taking the M2 upward, because these are constrained, right? This rope is not flexible. So how much ever M1 moves has to be the same as M2 moves. And with the same idea, how much ever M1 moves down or M2 moves up is related to how much the pulley rolls. Right? This rotational motion of pulley is not independent of the linear motion of M1 and M2. That's related. So there is alpha, which is the angular acceleration, which is related to A by alpha times R is equal to A. It's very similar to how a rolling wheel of your bicycle tire, how much it rolls is decided by how much you accelerate. If you're going faster, it will roll more, it will roll faster, and if it rolls slower, then it will move slower. And in that sense, it is related to the acceleration also. So all these are the connections. Let's begin with M1. What is the force equation for M1? That's going down. So it is, I'll put this in this direction. So it is M1. We have been actually consistently using top as a plus, right? So it is plus T1 minus M1G is equal to minus M1A, where I've introduced the idea that acceleration is downward for so it is going down. What about M2? That's M2 is plus T2 minus M2G, and that's equal to, now it's going upward, so it is M2A. Those were the two equations we were using earlier to calculate what would be the force of tension and the acceleration. And remember, again, the difference here, T1 and T2 is not the same, right? In the earlier analysis, when the pulley was massless, it was the same tension. Now let's talk about the pulley itself. Let me move this down. Okay, so now let's talk about the pulley. Remember, I times alpha, mass times acceleration, has to be equal to the torques acting on this. There is only two torques acting. That's torque due to tension 1, torque due to tension 2. That's the two forces that is acting on it, and each one will exert a torque on it. We have to specify what is this pulley made up of. So let's say this is a solid cylinder. So I have to specify that. So pulley is a solid cylinder. Pulley is a solid cylinder. Which means to say, if you go to the other board that we describe the moment of inertia of each of this object, that means this is half mr squared. M is the mass of the pulley, in this case m3. m3 r square, r is the radius of the pulley. So that's your moment of inertia. Notice a factor of 2 comes in. If it was a sphere, this will be a 2. If it was a solid sphere, this will be a 2/5. Right? So this factor has to be put in. That's something new one. Then there is m3, and then there is r square alpha. And what's the torque due to tension 1? So this is your pulley, and this is your tension T1, and that's your axis. Remember, torque is equal to how far you are from the axis. So that's your how far you're from the axis, force times sine of the angle between the force and the distance vector from the axis. The distance vector from the axis is this quantity in here, which is exactly the radius of the cylinder if you want. So T1 will be equal to, so this is tension T1. So that's R, radius, the length of this radius times T1. And sine of the angle between them, we said extend this way, and that's your 90 degrees. That's your vector can be moved this side, and that's your 90 degrees. Even if you take this to be the angle, that's okay, because it is sine of 180 minus theta is always sine of theta. So this is sine of 90, which is exactly equal to 1. So we have the torque due to the force of tension T1 to be just R times T1. So that's R times T1. Instead of forces, now we are getting a distance associated with it. That's the idea of torque. That means to say, if you're farther, you exert more torque. There is another torque in here, which is T2. And if you do the same analysis there, that's your T2, that's your radius R, that's again 90 degrees. So torque 2 is equal to R times T2 times sine of 90. And now I have to talk about a relative direction for the torque. Remember, tension T1, as we can visualize, makes this mass move in the clockwise direction, and this makes it move in the counterclockwise direction. So we have to keep that clear. This was negative. We said anything going clockwise will be negative, and this will be positive. So R times T1 will be negative. So that's negative here. And this is plus R of T1. So it's clear. This is minus R times T1 times plus R times T2. And the angular acceleration itself, we said, is moving in the clockwise direction. So that's negative. So notice the signs that is coming in. This direction here, this pulley is constructed, or I have built, I've talked about the problem as if it is moving in the clockwise sense. That's minus direction because of that. Force of tension T1 helps it move in that direction. So it is again minus, and it is plus T2 in the sense that it tries to resist that motion. It helps it in the counterclockwise direction. Immediately I can flip this if I want to, but let me keep it as it is, except that I want to divide it out by the radius R. So this is the same as 1/2 times M3 times one of the R's I'm going to cancel, which is there in each one of the terms, and that's R times alpha. I put that again in parentheses, and that's R times T1 minus T2. So I did two things in going in this step. One is I multiplied by a negative sign. So all these terms, each one of these terms changed sign, and I divided out by R. And whatever is left here, if you notice, that's nothing but acceleration. Since this pulley moves exactly the same amount as the mass M1 here moves down. So this acceleration A, it pretty much decides what is going to be the angular acceleration of the pulley, because the linear displacement is exactly the same as the angular displacement, and it is controlled by the radius R. So this is A actually. So overall, if I were to go back here, I had two equations, but now I have a third equation, which is T1 minus T2. And now I have half of M3 times A. A because R times alpha is nothing but A. So I have T1 as an unknown, T2 as an unknown, and acceleration is also an unknown. And if you allow me to erase these things here, but it has become a little more complicated than what we had earlier. We used to have two equations and two unknowns. T1 and T2 were the same earlier, and acceleration was also not known. But now we have T1, T2, and acceleration as unknown, but we have three equations now. This is from the force equation for mass M1, force equation for mass M2, and the torque equation for mass M3. So what I do now is that when it comes to second and third equation, I add. So that means to say, this is T2 and minus T2 will cancel out. But this one I want to subtract. So what I'm going to do is, let me write this down. So this is 3, 2, 1. So what I'm doing is I'm subtracting 1, right, minus of the first equation, plus the second equation, and plus the third equation. Right? That's what I'm doing. So change the sign of the first one, then add, then add. If you do these things, so that's equal to, since I'm changing the sign of the first term, first equation, so it is M1 plus M2 plus half of M3 times acceleration A. Each one of them had an acceleration. And when I add this, notice that there is minus T1 minus M1G, sorry, plus M1G because I changed sign. Then I have plus T2 minus M2G. And I have to add one more. So there's T1 plus T1 minus T2. A little bit of clutter there, but T2 cancels out and T1 cancels out. That was the idea of doing that addition and subtraction in there. And what I have is M1 minus M2 times G is equal to this whole thing out there, but I can divide that out. So that's divided by M1 plus M2 plus half of M3 is equal to the acceleration A. Once I know the acceleration, I know the angular acceleration. But notice what is the feature in here. This is what is the pulley related concept is in here. We are interested in the rotational motion, or what contributed to the rotational motion. If not for M3, if the pulley was massless, this will not be there, and I will have simply M1 minus M2 divided by M1 plus M2, which is exactly the acceleration that it would have experienced if the pulley was massless, which we did a few weeks ago. But now, since pulley has a mass M3 associated with it, so that is an additional term in there. But then it is multiplied by a factor of half. Since we chose this to be a cylinder or a cylindrical shell, it came out to be a half. No, since it was a solid cylinder, it came out to be a half. If I had chosen this to be a cylindrical shell, this would have been 1, and that would have been larger, right? Half of M3 is smaller than 1 times M3, and I can change this accordingly. So a larger M3 or whatever contribution you get in here will contribute to a smaller acceleration. So let me write that down. So very little space here. So I think so. If I had a solid cylinder, so solid cylinder gave me acceleration to be m1 minus m2 times g divided by m1 plus m2 plus half of m3. Let me specify m1 and m2 and m3. So let's say m1 is 10 kg, m2 is 20 kg, and m3 is 30 kg. All 2 significant digits, let us say. And let me also erase this. I think I copied that down, so I have more space here. So, oh, this doesn't help, right? M1 has to be larger than M2, so let me switch, right? M1 is 20 and M2 is 10. So M1 is 20 kgs and M1 is 10 kgs. So 20 minus 10, so that's 10 times 9.8, just to clarify so that you're not scared about the variables, and divided by M1 plus M2, so that's 30, so that's 20 plus 10 plus half of 30. That's how much angular acceleration we have. That's meters per second square. Sorry, linear acceleration A we have in meters per second square. But now let's do this for a solid sphere. The only thing that will change is, again, this factor in here. So that's M1 minus M2 G divided by M1 plus M2 plus, instead of 1 by 2, if you look into the solid sphere and the axis passing through the diameter, you have 2 by 5. So that's 2 by 5 times M3. So that's again 10 times 9.8. Everything remains the same. It's 20 plus 10. And 2 by 5 is 0.4. So that's 1. So 2 by 5. 2 by 5 times 30. In this case, this will be 15. So let me write this down. So that's 98 divided by 30 plus 15. So that's 45 meters per second square. And in this case, this will be 98 divided by 30 plus not 15, but 7.5, right? So it's 0.4, right? 4 into, so that's 12, right? 12, so that's 42. So it's relatively less in the denominator. That means angular acceleration will be more. So that's meters per second square. And I'll leave it like that. I won't get in the numbers. Primarily, it's very clear that if the denominator is larger, that means the angular acceleration is less. I'll quickly, very similar example. I'll do this for a single mass. That's also doable. So now let's have a very similar problem. We have a pulley on which you have a string that is wound upon this pulley, which can be released. Right? So there is a string that is already winded on this pulley, and you have a mass M that is hanging onto this pulley. Let's say this is M1 and that's M2. And there is a radius R associated with this. And this could be a solid sphere, let's say, solid sphere. And again, with all the understanding that the string is massless, the axis of the pulley is frictionless in those situations, we have now only two masses, M1 and M2. Earlier, there was another mass associated with this, right? But now this is going to rotate. Why does it rotate? And where is the other part of the string? This is wound, right? All the string is winded on this pulley. So as it falls, it is released off, and this is a perfectly possible motion. That is an acceleration A associated with this, and it will be exactly controlled by how much the pulley rotates. So acceleration A is equal to alpha times R, right? Where R is the radius of the sphere. It is the same as earlier we said M1 falls, so M2 has to move with the same acceleration upward. So the angular acceleration of the pulley is decided by how fast the M1 falls. In this case, now there is M1G, tension T, there is only one tension, so we don't have to specify T1. So, and this tension will actually pull the pulley, or will help in the rotational motion. So we immediately write M1G minus T is equal to M1A, right? We earlier said plus T minus M1G minus M1A, but if I change the sign, that's the equation you get. And now the torque equation for the pulley, there is only one torque T, and now I can make it faster. So there is only one torque, so it is T times R. And that is a sine of 90 degrees, but since this is acting right perpendicular to that, that's 90 degrees. So that's T times R is equal to I times alpha. Right? So that's I times alpha. I want to think of this, so let me write this equation here. PR is equal to I times alpha. Multiply this by an R and do that on both sides, and then identify this to be the acceleration. So tension T is equal to I over R squared. So I brought this down, and that is acceleration A, right? So this is acceleration A. We are saying this is a solid sphere, so that's the same as I, that's equal to 2 by 5 mr squared over r squared within the board, yes, and A, and r squared cancels out. So the equation I have is T is equal to 2 by 5, r square cancels out, times m, in this case it is m2, so that's m2 times A. That's your torque equation, right? There was only one torque acting, is equal to moment of inertia times the angular acceleration. So that's this equation, which can be re-expressed in this form. There's only two equations, so I can add them out. So tension T cancels out. That's M1G is equal to M1 plus, very similar problem like earlier, is 2 by 5 times M2 times acceleration. So acceleration is equal to M1G divided by M1 plus 2 by 5 times M2. Hopefully it's not too bad. 2 by 5 times M2. Once I have the numbers, I can actually substitute it in. And again, this helps us to analyze what kind of object should you choose for the pulley. Again, it depends on whether you are interested in the strength of the pulley, are you interested in getting more angular acceleration, or so on. It's like if you have a bicycle wheel, if you're designing a bicycle wheel, where do you want to concentrate the mass of the wheel on? Again, it depends on what exactly are you looking for. Are you interested in keeping the axis very strong so that it doesn't break away, or are you interested in having more angular acceleration? So that will be the difference between, let's say, racing bikes and normal daily use bikes. So those are all the factors that comes in, but this is very introductory.
Could you give us a extra credit question for today?
Oh, yes, yes. The question is, I was thinking about that, so actually change the question. Extra credit. Let's take two bicycle wheels. I was just talking about it. So we have a bicycle wheel, which is, this is a ring. That means to say that all the mass is concentrated at the radius. And the second is you want to have a disc. This is a disc, solid disc. Both are of radius r. Which one is more suitable if you want a higher angular acceleration? Like if you want things to be moving very freely about the axis, then which is better? And remember again, that's what I was just mentioning, that the problem depends on what you keep fixed. Right? Sometimes you keep the torque fixed, but that need not be always the point you're interested in. So the extra credit problem is that if everything else is fixed, which of these wheels for a bicycle helps you with the angular acceleration? So alpha, which gives higher alpha? Thanks for reminding me about the extra credit. Okay, that's all actually. Thank you.